Hey, so today we're talking about the chi-squared test of independence, and please go ahead and get Notebook 18 open and running. So the first thing you might ask is what the Sam Hill is the chi-squared test of independence. Well, chi, this is the lowercase Greek letter chi. All right, over here, this is a lowercase Greek letter chi. The main idea of this test is, hey, what if we have two category variables and we want to know if the variables depend on one another? This is the test we use in that case, okay? And those may be fancy words, but let's put some meat on the bones, right? What kind of test are we looking at? Well, in our personality data set, the data was collected at UNG Dahlonega a decade ago or more, and we asked students what their seating preference in class was. If there were seats available in the front, back, and middle, where would they prefer to sit in class? And we also got their age, so we divided the group into 21 or older, 21 years old or older, or 20 years old or younger. Okay? And is there a difference? Is there a dependence? Does the place where they like to sit in class depend on how old they are? That's the type of situation we're talking about, okay? Now, just to let you know that traditionally these types of tables in statistics, they go by two different names. Sometimes they're called two-way tables because there's two category variables. We have age horizontally and class seating preferences vertically, but we've got two category variables called a two-way table. The other thing it's known as is called a contingency table. And I think you'll see why I mention that when you see, oh, the way we run it is we use stats underscore chi2 contingency, chi2 underscore contingency. Okay, and again, the chi, chi, refers to the Greek letter. And okay, but what's this stuff? Okay, so this two-way table actually has the observed data, right? So whatever was observed is in the two-way table. And we have to code the two-way table into Python so that it knows what the data was. Okay, so notice that inside the square brackets, the first square brackets, the 28 and 17 from the first row. And then inside these second square brackets is the second row, 40, comma 16. And then the third row is 16, comma 12. And then square brackets around the whole thing and parentheses around the whole thing after that. Why? Well, you'll see when we run our first chi-squared test that this actually does in fact create a nice table or matrix. It looks like a matrix in Python. And then once we have that data, that's all Python needs to run the chi-squared test, and it will spit out some interesting information. We'll talk about that in just a second. So let's go in to our notebook, and I'm here on the Notebook 18 chi-squared test of independence. And I'm going to do one thing. Do you see this import scipy.stats? I'm going to do as stats. I'm going to create this alias stats. Do you need to do that? No. There are some other ways to accomplish it, but future notebooks tend to be that way. Okay. And I want to show you how this works. So I'm going to jump back into our, how to code it. All right. So let me just copy paste this, jump back into the notebook. Right? So this np.array, and I have the three columns. And let's actually type OBS in here, and we can see, oh, and see it, look, it does code it up as a three-column table, two-column table and 3 rows, exactly like it was. And then I can, in fact, run the stats.chi2 underscore contingency. And I just tell it, hey, the little matrix I just created, its name is OBS. And then what the Sam Hill does all this output mean? Okay, you won't have to know this. The stuff coded down below actually names some of these things. This is our test statistic, our chi-squared statistic. This is our p-value. Notice that this p-value is greater than alpha, so 0.38 is greater than 0.05. So we're going to fail to reject the null, and we don't find a difference in seating preferences based on age. And then this array is the expected table. So we have the observed data table up here, and this is the expected data table, which if you're going to do it by hand is necessary. But those are the two steps. We have to create this observed data matrix, the two-way table or the contingency table, and then we just call stats underscore chi2, excuse me, stats dot chi2 underscore contingency. And that's how we run it. And we'll talk about how to report out in just a moment. So example one in the notebook is this randomized control experiment. We have a treatment group and a control group, and the treatment group are receiving Botox, and they're trying to control the pain of migraine headaches. And so we're reporting on whether or not they experienced relief from the migraines based on whether they're in the control group and did not receive any treatment, or whether or not they were in the treatment group. Okay, that's interesting. And if we look at the table, we say, oh, now this makes sense. There were 16 people in the control group, and only 2 of the 16 experienced relief. And there were 15 people in the treatment group, but 9 of the 15 experienced relief. So it looks like that's an interesting association that we can take a look at. And here are the hypotheses. So for chi-squared, we generally just write these down instead of using mathematical symbols like we did for the t-test. So the key idea is that the null hypothesis is, hey, the variables are independent. So whether or not you experience relief from the migraines depends on whether you were in the treatment group or the control group. And if we reject the null, the alternative is that experience relief from migraines does depend upon the treatment group or control group, whichever you were placed in. And by the way, this is the one that the researchers want. Like if you're working for a pharmaceutical company or a medical company that's trying to develop a new treatment, right? You want to reject the null when you're testing your treatment. You would like the treatment group to do better in terms of experience relief than the control group. Okay, so if we reject the null, we'll be getting the result that the pharmaceutical company wants, or the medical research company is hoping to get. Okay, so same thing as before, we will create an OBS table, right? And it's got 2 rows, the 14 and 2, that's the control group, the 6 and the 9, that's the treatment group. And then we run the test the same way, stats.chi2 underscore contingency, and we take the observed data table and shove it right in there. The contingency table goes right in there. So let's get rid of the markings and jump into the notebook. Okay, so randomized control experiment, and they go ahead to explain the same thing. Now we're entering a table. So we can see the control group, results of 1 mean that they did experience relief, results of 0 means they don't. And then we see the treatment group, there are more 1s in the treatment group, which we noticed above. And we're actually going to look at a bar graph. So we have this nice table. The contingency table sort of is there, called tab. And then as a bar graph, we can see the pattern. And it appears that the gold, it is true, the gold represents those who experience relief, and blue represents those who experience no relief. And there does appear to be a pattern, a strong pattern, right, where there's more relief experienced in the treatment group. But this is an association. This is not a scientific conclusion yet, right? That's why we run the test, because this looks like a good association for the marketing folks. They'll be real happy. They'll be able to sell this treatment. Okay. And by the way, the notebook actually does a slightly different aliasing, so that chi-sq is available. So if you did not import above, you can import that and this will work. Notice that here you probably have the chi-sq. I've replaced it with chi2 underscore contingency. And you might be asking, well, why in the world are you doing that? Well, because in future notebooks on the project, for example, you may need to use this form. And I want you to be aware of that it works the same depending on what the aliases are. And sorry, it went below. So it gives us the chi-squared value. It gives us the p-value. It gives us the expected table. So the observed data table is still here. It's up above, right? The observed data table was coded in right there. And this is the expected table, which is helpful if you're doing this by hand. You can check your work. What does the results mean? Let's jump back in. Well, we have a p-value that's 0.017, which is less than 0.05, which is our standard alpha. So they didn't really give us the alpha level. So we always use 0.05 ever since Ron Fisher and the lady tasting tea example. He started using 0.05, and it turns out that that works pretty well. So we have a p-value that's less, and we reject the null. So the medical company is happy about this. Why? Because the evidence suggests that treatment works. Now, what the evidence actually suggests is that the relief experience does depend on whether the participants were in the treatment group or the control group, which is why the notebook made such a point of going through all the different things that could happen, right? Because this bar chart is really, once we know that, yeah, there is a difference, which group would you rather be in? Well, I'd rather be in this one where there's a much higher chance of success. And again, now that we have these statistic results, we know because of this p-value that we have evidence that the treatment does work. Okay, and what's this? This is the chi-squared statistic and a chi-squared distribution, and you can see the red, this is the small p-value, just this tiny bit of area under the curve that is shown. And what's going on here? Well, 9 of 15, 60% of the treatment group experienced relief, and only 12.5% of the control group experienced relief. 60% in the treatment, 12.5% in the control. And that's why if you read this carefully, they say, hey, we do have evidence that it was better to be in the treatment group. Okay, ready to be in the treatment group. And then the next thing we have is the Titanic data. There are a few theoretical points about the chi-squared statistic that are listed here. And I'm going to jump into the Titanic example, okay? So did your biological sex determine whether or not you survived the Titanic? And so this is rather a morbid example, but we all know the Titanic was a major disaster, right? And so we have survival, no, yes, and we have biological sex, male, female. It's listed as gender, but that's fine. We know they were speaking of biological sex. And so let's take a look at this, right? These are two categorical variables, and we can analyze this with a chi-squared. And our null hypothesis is going to be that, hey, survival rates on the Titanic were independent of biological sex. And the alternative hypothesis, if we reject the null, we're going to have evidence that survival on the Titanic depended upon biological sex. And we're going to do the same thing as before. We're going to create an observed matrix that has these numbers in them, right? The 1364, 367 in the top row and 126, 344 in the bottom row. And we're going to run the chi2 underscore contingency on that table. Let's do it. Let's check this out. So Titanic data, and the very first thing we do is we create a table with those numbers. They're the same as were on the slide. And again, we have blue is not so good, gold is good. And we notice right away that the chance of survival was there's a lot more gold than blue for the females and a lot more blue than gold for the males. What does that mean? Well, let's take a look. Okay, so now what's going on? We're creating this Titanic underscore agenda array, exactly like we said. It's got the male data in the first row, the 1364, 367. It's got the female data, 126, 344. That's the exact contingency table we had up above. And again, you can run it as chi-squared because of what was imported. And you will get the exact same thing if you run it as stats.chi2 underscore contingency. Boom. Okay, and then look at this p-value. This p-value is small, 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 tiny, tiny, tiny. What does that mean? Well, I hope by now you know that that means that when we have a small p-value, we're rejecting the null. And p is essentially 0. I mean, 10 times negative, 10 to the negative 101 power. Yeah, that's pretty small. That's way, way smaller than our 0.05 alpha. So we reject the null. And why did I say strongly suggest? Evidence strongly suggests? Well, because this p-value is so small. We don't just have evidence, we have strong evidence that surviving the Titanic disaster did depend upon biological sex. Now, some of this is cultural, right? Because, you know, back in the 1920s, they really did do the women and children first, right? That was the mantra, and they did live by that. And so the men were standing back and allowing the women in the lifeboats. That was exactly how they were trained in this particular situation. So there was also an interesting thing that happened with the class of ticket that was purchased, which is what we'll look at next. So this situation is very similar in our research approach. Does class depend upon, does survival rate depend upon class? And here's our two-way table, our contingency table. And again, we're going to have to code this in. And we are going to, run the chi-square contingency just like before. You can see it in bold down here. Okay, our null hypothesis is that these survival rates are completely independent of class. And the alternative is no, the survival rates on the Titanic depended upon class of ticket purchased or whether or not they were a crew member. So we will be taking a look at that. All right, let's do this. And the first thing we're going to have to do is create this observed data into a table. Okay, so let's, I'm sorry, my notebook has stopped. So give me a second. I'm going to pause the video. So here we go. I've restarted my kernel and gotten back. So here we're creating the observed data, and notice it's called Titanic underscore class. Okay, and we have this array, and you can basically see it here. There's a little bit of stuff added to it in this table, but it's the exact same numbers that we need. Okay, and then this is where we run it, right? And we run the chi-square on the Titanic underscore class. And when we do so, we get the expected table and we get a p-value. Notice that that's basically 5 times 10 to the negative 41st. So that is less than alpha. So here's our results for the class versus survival. We create, now again, this wasn't observed this time. It was actually Titanic underscore class, but we have to create this observed table, run the chi-square underscore contingency on that observed table, and the p-value is really, really small. Is that right? Yeah, times 10 to the negative 41st. Okay. And sorry, so the p-value is essentially 0. That's much, 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 much less than alpha, so we reject the null. And evidence strongly suggests that survival of the Titanic disaster depended on class. Now, does this mean they were actively discriminating against the lower class passengers? I think the explanation goes that the first class tickets were higher up and closer to the sides of the boat, right? They had windows, they had a better view, and just because of that, their location was closer to the lifeboats. And then second class, they were further towards the center of the boat and lower down. And then third class was, in the belly of the boat. So the third class passengers were just further away, sadly, from the life rafts. So that does help explain what's going on. Um, there is this interesting example that we use, class versus sex. Um, did um, and we already know that the survival rates depended on both biological sex and the passenger's class, but is there a relationship between class and sex? Okay, so let's jump in here, and you can see the reporting out is exactly what I just said. Okay, that yes, we reject the null. There is a statistically significant relationship between the class of ticket and whether or not they survived the sinking of the Titanic, and you can see in the bar chart here what's going on with the previous example. Now, this new example just runs, and oh my goodness, look at the p-value, we reject the null. So what the Sam Hill is going on? Is there a connection between the biological sex and class of passenger? And the answer is the chi-squared test actually says, hey, there's a significant connection between the two. But we aren't seeing a relevant connection. This is not something we want to pay attention to. Why? What's going on here? Well, it was a different time. This is 100 or more years ago, and different sociocultural norms existed, and fewer women traveled, and it was very expensive to travel on the Titanic. So there were more females in first class percentage-wise than there were in third class, for example. Very few crew. But that had a lot to do with the different sociocultural norms. Am I saying those norms were correct? I'm not. I'm just saying that there was a different sociocultural norm. Okay. And so this is not relevant. This class versus sex connection is not relevant. And the notebook says that the statistical analysis is fatally flawed. Okay. But it is an interesting example to look at the Titanic. And the notebook finishes reporting that out and talks about the confounding variables. Okay. And then it runs one of the earlier examples using simulations, which I'll let you take a look at. Thank you. I'm done presenting on the chi-squared test of independence.